Today's lesson is on ionic bonds and compounds. So, how do ionic compounds form? We've talked about elements. We've talked about how elements can form charges in the form of ions. Well, ionic compounds, right, these are compounds that are made from ions. It's just simply the adjective of the noun there, right? So these are coming from ions. So how does it form? Well, you have two oppositely charged ions. It means you need a positive and a negatively charged ion. It can be more than +1 or -1, but it needs to be oppositely charged. They combine in ratios such that the overall charge on a compound is 0. It's always between a metal and a non-metal, or non-metals. So your first thing will always be a metal, your second thing will always be a non-metal. The one tiny exception to that is if we get an ammonium ion, but we'll talk about that later on. If you have a metal that combines with oxygen, we call those compounds oxides. These are the things that you typically think of that are rust. So iron oxide is an example of rust. Okay, it's a metal oxidizes over time if you leave it exposed. If a metal reacts with another nonmetal, we call that a salt. So that's what's going on actually here in this picture. We have sodium metal and chlorine gas. Chlorine gas's formula is actually Cl2, and that reacts in there, and that's going to actually give you table salt. Both of those things in there are really, really bad for you, pretty toxic stuff. But once you let it react, right, you get table salt. So that piece of sodium metal and chlorine gas, both pretty bad. Salt, okay. Binary ionic compounds, these are the ionic compounds which contains only two ions that have combined chemically. So it's really, really straightforward. Just one of each. The example here, sodium chloride, NaCl, that's table salt. MgO, that's magnesium oxide. That's what you get when you burn a strip of magnesium. Sodium fluoride, that's a 1-to-1 sodium to fluorine ratio. That's actually found in toothpaste. Potassium chloride, KCl, this last one here, again, just 1-to-1, 1 potassium to 1 chlorine. That's sometimes actually given as a prescription for people with low potassium levels. So what about ionic compounds that are not binary? So what happens if we start getting more complicated than just 1-to-1? What ionic compounds might form from, say, calcium ions and fluoride ions? Well, from our previous lessons, you know that calcium is in family 2A and fluoride is in family 7A. And if we take a look at those families, we know that family 2A forms +2 ions in ionic compounds, and fluoride is part of the halogens, and the halogens form -1 ions in compounds. So we end up with these ions down here of a calcium +2 ion, right, and a fluoride with a -1 charge. So when these things combine, right, the overall charge on a compound must equal 0. Well, this one's +2 and this one's -1. So if I end up with something like CaF, I would still have a net positive charge because that calcium had +2 and the fluorides were each -1. So what we actually get isn't that, so we don't wind up with this as a formula. What we get is two fluorides combine with a single calcium there so that the overall charge is 0, right? This one, there's +2 coming from the calcium, and each fluoride is -1, so that's a total of -2, right? And that would cancel out. So that's how we end up with the formula for CaF2 there. Okay. What about aluminum ions and oxygen ions? Well, for these ones, aluminum is in family 3A, so we get a +3 charge. It's going to lose 3 electrons and get a +3 charge, and oxygen is in family 6A. We'll end up with a -2 charge. Well, in that instance, it's kind of a little clunky there because if you have one of each, right, if I had, for instance, ALO, okay, I am having one +3 charge and one -2 charge, and so if my formula was ALO, I would still have a net +1 charge. So what we have to do to fix that is have multiples of each of these. Up here we only had one calcium, but down here there's no way to fix this other than having multiple aluminums and multiple oxygens. So what you're looking for is what's the least common multiple of 3 and 2? Well, that would be a total of 6. So what we want is a total of +6 charge and a total of -6 charge, and that +6 and -6 should cancel out and give us an overall charge on this formula of 0. So in order for that to be the case, right? If each aluminum is +3 and I need it to be +6, that means I need 2 of these, right? And oxygen, if they're each -2, that means I need 3 of those to give me -6, so that the sum of all my charges in the compound is equal to 0. Well, so that formula then is Al2O3 written like that. Okay, so that's how we figure out the formulas for compounds. So if I tell you to give me the formula for a compound between aluminum and oxygen, okay, you go look and see which families they are. You can figure out the charges. And then from there, figure out what the formula for the compound should be. Another way that some kids sometimes look at this is, well, this is a 2 and this is a 3, so what I can do is just swap them. So this 3 goes over there, this 2 comes over here. In general, that can work. You do have to be careful, though. Sometimes you end up with ratios that need to be simplified, but you can do that for the most part. What about ions that include more than one atom? These are called polyatomic ions, and you should be getting or already have a polyatomic ion sheet, okay, or just an ion sheet that's going to have a lot of ions on it. So it's really easy when we're just looking at families, and that's what we've been doing the last few days. Right, families 1A, 2A, 3A, 5A, 6A, 7A, and what charges they have. But there are some ions that are polyatomic, so poly meaning multiple atomic atoms, so many atom ions. There's a list that you need to become familiar with, and that's the list that you should be, again, already given, or the list that you are getting currently. There are names and charges for these things, so you'll be given a sheet of them to study there. So for instance, this one, okay, it's a negatively charged ion, NO3. It has a -1 charge, okay, NO3, and that ion's name is nitrate. Okay, so if you go look up the ingredients on some food labels, you might see stuff with nitrates on it. This one is SO4. It has an overall -2 charge. Okay, so the whole thing has a -2 charge. All 5 of these atoms, 1 sulfur and 4 oxygens. And by the way, we don't split these. These get stuck together. We can't split apart polyatomic ions. That SO4 -2 ion is called a sulfate ion. This last one here, CO3 with a -2 charge. Right? So it's got a -2 charge. This one is called carbonate. And again, the list that you're getting, you should become familiar with those. Some you're going to see more often than others, and hopefully within a few weeks you'll be familiar with all of them. Okay, so that's how they form. What's their structure? Well, what we end up having are these crystal structures. We call them lattices. Positive and negative ions exist in repeating patterns and shapes. These are called crystals. So over here you have an example of a sodium chloride crystal. You can see alternating sodium ions and chloride ions here. It packs nicely into this kind of cube shape. Not all of them do this. They have other shapes as well. Okay, but this one kind of neatly packs into a pretty straightforward cube shape. A crystal lattice is a 3D geometric arrangement of particles. Okay, so that's what this is over here. This is what, if you could zoom in and look at the compounds, they form a crystal lattice, something like this. Not always necessarily cubic, but some other repeating three-dimensional geometric arrangement. The shape of crystals varies depending on its chemical formula. Here, right, sodium chloride, the formula was NaCl, so you have a 1-to-1 ratio. So for each sodium, you got 1 chlorine. But if you had something like, say, aluminum oxide, which we saw just a moment ago, okay, the way that's going to pack is going to be a little bit more complicated than this just alternating positive and negative ions over here. And we're not going to get too much into that, but just know that that's how what the crystal structure is determined. The physical properties of ionic compounds, their melting points and boiling points and hardness all depend on how strong the attraction between the ions is. Some of these are fairly low to the point where you could, actually melt an ionic compound, say in like an oven. Others of them are extremely high, and you're going to need a torch that can get pretty well up there in temperature before you can melt it. Electrical conductivity depends on the ability of charged particles to move freely. So if you saw just a moment ago with that crystal lattice, those particles are locked into position. Remember, those are solids. And if you remember what solids were from previous chapters, okay, those particles are locked into a position. So in order for you to have electric current moving through it, there's got to be some mobility of those charged particles. So in a solid state, okay, those ions were locked into a crystal lattice. Again, that's what we saw in that picture on the previous slide. They can't move. So the result of that is solids are poor conductors. Okay, they do not conduct very well. In a liquid state, though, so if you can heat up the ionic compounds, now things are free to move around. Or if you dissolve that compound into water, the ions are now moving. Okay, they are dissolved, they are separated. And these are good conductors, so we call those electrolytes. And that's why there's a difference here. In order for something to conduct electricity, the particles that have a charge have to be able to move. In a solid, they're stuck in position, but in a liquid, or if you can get them dissolved into the separated ions, you're going to have good conductors. Okay, so back onto the melting points and boiling points. Ionic bonds are relatively strong. Therefore, ionic compounds have high melting points and boiling points, some higher than others. So here we can kind of see melting points: sodium iodide, NaI, 660, potassium bromide, 734, sodium bromide, 747. Okay, and all the way down here. I do like to point out this last part, MgO. Notice it's significantly higher than the others, and that factor is actually because the rest of these are all either +1, -1 compounds, right? Sodium and iodide. The sodium's a +1 charge, the iodide's a -1 charge. Potassium potassium is +1, bromide's -1. The calcium here is +2, and the chlorines are each -1. But down here, this magnesium oxide is +2 and -2 for those ions, okay, based on the families they are in. And notice how much of an effect that has on the melting point. Shoots it way up. Okay, for a hardness of a ionic compound, crystals are hard, rigid, and brittle, so meaning that they don't bend, they just eventually break when applied with enough force to it. So to break a crystal, force must break the charge between the ions. Okay, so remember we have alternating positive and negative charges, not always necessarily in a cube shape, but they are going to be alternating there. In order for you to break apart a crystal, you have to break that attraction. You have to apply enough force to it. So say like with a hammer that would weigh enough. And when you apply enough force, what you do is you misalign the charges, and now you have like charges next to each other, and these two things are going to repel. One's going to go one way, one's going to go the other. Okay, when you have those charges, the like charges next to each other. And that's what we see happen over there, is that it's broken apart. It's pretty hard to get back together because it would need to be exactly how it was before in order for that to work. A couple more terms here just to know. When compounds form, they can absorb energy, which is endothermic. What you should think about is energy in, right? Endothermic is energy in. And those reactions are going to make something feel cold. It absorbs energy. So the actual reaction, if you touch it or you're near it, it's going to feel cold. That's how you get these kind of instant ice packs, or with reactions that are endothermic. Or they release energy, which is exothermic, which means, right, energy is going out. Okay, and those are going to feel hot. They're going to release heat. Most reactions, not all, but most reactions are exothermic. When you carry them out, they release heat, so you can get those like instant hot packs or like hand warmers. Okay, so you're doing a reaction that is exothermic. There are a few endothermic reactions, but there aren't as many as there are exothermic. When you're going to form an ionic compound, though, that reaction is always exothermic. So that picture we saw at the very beginning that had sodium metal and chlorine gas reacting, that is definitely exothermic when that goes to form NaCl. That is a very, very exothermic reaction, releases quite a bit of energy. So all of these ionic compounds forming, they are going to be exothermic, right? They are going to release heat.